I'm going a little bit ahead in the steel construction. I'm seeing where steel will be heading. I understand India is a little bit behind from what Mr. Hadkar and Jindal mentioned. Obviously, the steel is not as ahead as we would like it to be to compete with the Western and other South Asian countries. But it's just a process. I believe India will have to play catch up very quickly. So basically, first thing, what I'm more geared into the design process and how we can expedite the steel design, so it can help this lead time, which typically steel would require. Typical process is an engineer will prepare the tender documents, and a steel contractor will review those drawings, build his 3D model, design the connections, and then fabricate, detail, fabricate, and transport. So what we are trying to do is expedite that process so the steel contractor could be involved early on along with the steel the engineers of record. And if the client gets the entire team together along with the steel contractor, then that is very much possible. So first, we being engineers, we are always looking for codes and guidelines. So the first question is, are there any industry guidelines? There are very few documents which kind of detail how a building information modeling should be done, which we in the short term call it BIM. And I don't believe there are that many documents in India, but I believe there are enough documents in the Western world, and we can use some of those. I'm not going to go into detail of those documents, but there are enough documents which basically help the structural engineer and the steel contractors. So first thing we all need to ask ourselves is, when you want to make a BIM model, what is the real use of that model? Is it just for the structure? Is it for the architectural and mechanical engineering, plumbing coordination? Is it just for construction reference? Or is it just for the contractor's use? Or it is really for the owner who is going to keep that model forever, and as he proposes more changes, he can use this model and update. So first thing we need to know is we need to have a meeting with the entire team and understand what are the goals, what we are trying to achieve, and how we can meet these goals. Of course, these goals will be different from project to project and clients' needs. So once these BIM modeling criteria is established, we can move ahead. There are different, I don't know how many are structural engineers over here, but there are different phases of design. One we call it as concept, design development, construction documents, fabrication, and final will be as-built model. And then once we understand what are the uses, we can plan to rope in other team members and build the BIM model accordingly. Obviously, the biggest advantage of a BIM model is reduce the time, which, like as Mr. Hadkar mentioned, even though the cost of land and building construction cost is there, but I believe time is the biggest advantage for steel, where construction can be expedited, steel is still lighter, and it can be a win-win situation for everyone. So these are just different ways in USA we determine and we process with the design for steel projects. So basically, what does all this mean? We need to make sure that with steel, the accurate and precise grid system, because steel, as concrete, steel cannot be very forgiving. It needs to be dimensioned to very small, couple of millimeter, tolerance is all we have. So we need to make sure a model is built properly, because if there are errors in the model, everyone will start on a wrong track and we can have a lot of problems. But basically, so a BIM model, since it is a computer developed program, it gives you a very precise and accurate grid system. We can define the members, its location. We can even have a metal decking and what kind of detailed connections we need. These are just some complete models. Whether it's steel, concrete, doesn't really matter. It just gives you a complete 3D picture. So when you start ordering the steel, in the steel project, there are 3 phases we break the steel design process. The first one is mill order, and the mill order is needed, which is for rolling of the section. That is needed way early because obviously it takes time to roll the sections, and depending on the size of the project, the size of the members, sometimes you can buy them ready off the shelf, or sometimes you need to kind of get your order in line so it can be rolled. And for all these, the digital model will be used. So basically, members should be modeled properly. You need to define the grid line, the top of center, column locations, whether they are continuous, the beams are continuous. All the works needs to be designed and defined in the model. And then, as you see, there are 3D models which are developed, different colors, define different grades, different sections. And then basically, the model is built and then you can produce it into drawings, which can be used, given to other trades. So now in these, basically we show all these 3D different trades going in. The structure is basically, it's an entire 3D model of entire structure, and different trades also can provide their input or use the steel structure to see if there are any clashes. And you can keep on updating. The easiest thing is it really doesn't take much time to update these models. So beyond the design and detailing, after a structural engineer designs and details, what we can do with the 3D model. And basically, other construction trades can use this model for their coordination, class detection. It could be used to the facade engineers. They know exactly where the structure is, so based on that, they can define their geometry and prepare their connections. All the exposed, there aren't that many steel buildings in India, but now the latest trend is with the contemporary structure in Middle East, in West, to keep the steel exposed, especially if it has certain floor-to-floor height. The fire codes are not very stringent, and you can make the welding, bolting of the steel very pretty and make it an architecture. And that's why these kind of models are very important, because the architects can really understand what the final, with the bolts, what the connection will look. I remember I worked on baseball stadium, and we had to design. The architect, we told the architect, we showed him drawings what the gusset plate size would be. But when you look at all the drawings, it's really not very clear. And then we were visiting, we were walking at the site, and the architect looks at me and is like, Anjana, what are you doing? What's going on? I don't like this big steel plate. And I'm like, Bob, these plates were there from day one. Didn't you see it? And he was like, yeah, I saw them, but I didn't really realize they were going to be this big and ugly. And we said, okay, so then we had to come back and make some notches and make the plate pretty. Thank God we had asked for a mock-up, so there was only one connection. So after that, all the connections were fixed. But these kind of problems would not happen if you really see a 3D model, because then you really are looking at the complete picture. So it really makes a big difference. And then along with that, a structure cannot be just made up of steel alone. No matter what, you'll still need walking surface, which is concrete, could be precast concrete. So along with the steel, when you put the precast concrete and all that, you can see all the clashes the model can have, the structure can have. It could be rectified before you get into construction. So it really saves a lot of time because there is no fixing to happen. Then we call the second phase, we call it a collective model. Once the basic steel members are designed, we order for mill order, then we say, okay, now let's just do the design portion of connections. And once a structural engineer, they know what the forces and everything is, so then you start into the design of the machine. So the connection design, I mean, it can be pretty extensive steel design, and obviously it affects the fabrication and erection because that's how it needs to happen, how two members are connected. So we start with the engineering of the connection. Sometimes we do the complete engineering. Now, Honorable Kamasetti, we kind of request the clients that we understand the forces, we know exactly how the structure is working. So rather than getting a steel contractor design the connection and discuss about how the structure is working, it's just much easier for us to design out the connection, and then they can take it from there and detail their shop drawings, where they will worry about the tolerance, the buildability and all that. But in general, we have enough experience with the steel design that we can give them almost 90% complete design. And then the models, the BIM model will show all these connections. As you can see on the photos, you can see every picture with every bolt weld in the model. These are just some of our detailed structural drawings. Even though we show it on the model, we still put it on the drawing. So in case if anyone wants to refer to it walking on the site or just wants to have it record, they can still see what's going on. Again, these are some connections, very detailed connections, and then the design. Tough times reading this. Okay, so after the connections are all modeled, then we go to phase 3, which we call it as drawing extraction. Basically, what it does is, we have to dedicate a fabricator, and then typically a fabricator will give this to some detailer and engineer to kind of finalize the connection designs. But we feel that if a structural engineer of record performs all these, then we can make all our connections, which is in our computer model, on the drawings. And basically, to really help all the entire process can speed up the schedule and just a positive thing to happen. And once the connections are also all designed and modeled, the preparation of shop drawing becomes very easy, because for that the fabricator doesn't need an engineer. He just needs someone who's experienced enough to understand the model and extract it in form of shop drawings. The new trend nowadays is that it's pretty much everything is going to be digital. So from the connection design from the computer, they can just transport all the information into the digitized machines, and the steel can be all fabricated without any people. But I think it's going to take some time, so we don't have to worry about the jobs yet. And basically, this way, the shop drawings are all done, and then the fabrication and installation process gets started. These are again some examples of some of the projects we have done, and it just shows that these are not simple run-of-the-mill kind of boxy sections. These are very complex structures, and I honestly cannot imagine how these can be built in concrete. It's just got so much geometry variables that it is almost impossible to make it in concrete and make it this light and airy. So basically, in the old time, we used to have a real, very linear kind of team where the owner will hire the architect, and the architect and owner together will hire an engineer. Once the drawings are finished, the contractor, fabricator, and detailer will come on board, and then the building gets built. I don't think my video is working for some reason. Okay, it's working. So now the new way is, I don't know if you can see the color. if you see the engineer and contractor are kind of working together, and it just saves this linear time, the time what the contractor used to do to get it to the fabricator and detailer, it's all changing. So basically what it does is it really saves a lot of time, and 3 to 6 months in a construction schedule, as you all can understand, is tremendous savings for the owner. And then basically it's the same kind of process for request for information. Sometimes there are changes in the design, maybe something got missed, but all that process happens during the design, so it doesn't hold up the project during construction. So in this process, basically, instead of following the linear pattern, it's basically everyone is working together. And it really saves a lot of time. So the entire workflow, the design and detailing is really going parallel, and it can eliminate, I don't know about India because I don't have much work experience over here, but USA, I'm residing in USA, and it's a very litigious country. Any change, there are always lawsuits, so you really need to protect your owner because he's the one who has hired you. And you need to make sure that at the same time you have to sympathize with the contractor, because you can't be making changes and assume that he will be taking the loss, because we all are here to do business and everyone needs to be profitable to continue running the business. So we need to make sure that there are least changes, because once there are changes somewhere during the construction, it's a problem. Whether it's a problem for the owner, for engineer, architect or contractor, it is a problem. But all this detailing process running parallel with the design, it solves all these problems, and the workflow is pretty fluid, smooth, and there are really not an issue. And considering in this new time and age, structures are becoming very complex. Just yesterday I was in Mumbai and driving by BT station, and I look at this amazing building, and sometimes I feel like I'm glad I wasn't born at that time, because I don't know, if I had become an engineer, I don't know how I would have built that building. So I understand buildings, amazing buildings were built in 1800 century or early 1900. But now, none of us have any time. Everyone is on a very fast-track schedule, and the structures are becoming very complex because everything is computerized. People are expecting us to design everything faster, deliver it faster, and finish it faster. So because of all that, these processes, we need to advance in the technology so we can really keep up with the pace of what our demands are and what we can deliver. So again, basically in this one, it's just trying to compress the entire schedule. So detailing activities during the design phase, so it shortens the schedule, and you can really avoid the entire schedule and any kind of delays. These are some of the projects I have worked on. This is one of the, I believe, world's most expensive football stadium. So this for New Jersey Jets and Giants teams. It can sit about 80,000 people. In my experience, this is one of the fastest projects. It has 25,000 tons of steel. We won the project, and the minute we won the project, it has a very jumbo large steel column sections, because this is what stadium which had about, I would say about 18 to 19 meter column spacing throughout the stadium. It has a very high-end finishes and a pretty tall structure for a stadium. It's got 8 levels. So the columns were way above what the normal mill order sizes USA really fabricates rolls. So we have to go to trade hour. That is the only steel rollers who build larger sections. So and they have very limited days. They roll only on certain days. So if you go on their website and you find out that you need release the entire schedule in December. We won the job in November. The architect didn't even pick up the pencil to design the building. He just had some cartoon drawn. And basically we had to start to order steel. So I had a team of 15 engineers working. I remember it was before Christmas time, which for me is not a great holiday or not a big holiday, but all my other colleagues, they celebrate Christmas, and we had to sit for 2 months working till 4 o'clock in the morning every day, 8 o'clock in the morning, everybody's back, and we designed about 8,000 tons of steel in 2 weeks, talking to the architects without really getting drawings, making some good assumptions, and we placed an order. And if we had not placed that order, the next schedule would have been after 8 months. So the job would not have been built, or we would have to look for all the fabricated latex sections, and that would have taken a lot more time. So not only we were able to design, but 2 weeks putting the whole team together, we were able to order the steel. A lot of times people are a little bit negative about ordering the steel, that you cannot come back and change. But if you know what you're doing, if you're a good engineer, you can do it. Then of course there were changes, and of course we had to make some changes. But we were literally, if we thought the column was supposed to be here, we were able to use somewhere else. And maybe there was a little bit of wastage in the material, but we were able to save 8 months, which was far, far more important than losing 100 tons of steel. In USA, the stadium, especially the sports facility or any of these kind of venues, are very critical because they have their opening date is set in stone. Every delay in a day can cause huge penalties to the contractor. So this was a design-build project where the contractor was also on board, and that's why we were able to order the steel. So basically, the entire job was about 27,000 tons of steel. It was from the start of the design to the construction completion. It was 27 months from, like I say, schematic topping out. Actually, it says topping out. That is right, but we started releasing some of the lower floors architecture. And basically, it was 3 to 6 months ahead of schedule. And when steel is ahead of schedule, there is a huge benefit because usually the steel and concrete is leading, because that's the first shell is the first thing we have to build. And that means if there are any other delays in any other trades, if steel is 6 months ahead, you are not a breathing room to accommodate other changes, other delays. If steel gets delayed by 6 months, you know that all you are going to face is delays and delays and more delays. So these are just some of our 3D models. As Quantum Thomas said, we do every project, whether it is a small stair opening we are working for a client in an existing building, or a large project like this, we do everything in 3D, and now we are going to build. And then after we started Meadowlands Stadium, we were contracted, our scope was just to make the steel structure for the building. But then once they started realizing the bleachers, the seating area were made of precast, and they realized that there were so many mechanical utility pipes, steel connections and all that they felt that there would be a lot of clashes. And since precast is also made beforehand, they couldn't afford to have any clashes. So they kind of increased our scope, and they told us to add the precast bleachers also in our model, so they can really check everything, all of the trades also for clashes. And if you see, this job was only 60 tons of steel, but it was a very complex, very light, airy kind of structure, and we had to do BIM because otherwise we wouldn't have been able to design the connections. This is an airport hangar, so obviously it wasn't a very high, architecturally a very, critical project. But doing this kind of modeling beforehand really makes the job project complete faster, and it can really help one. These are just some expressions of modeling to drawings. This was Yankee Stadium. For this one, we were hired to design every single connection, which again helped the project to complete it on time. So besides designing the buildings, the other use steel has is even during construction. You know, it really, like for a large venue, let's say if it is a concert hall, it's got an uninterrupted large roof, and obviously if the roof is built of steel, sometimes it's not possible to design, or even if you design, to fabricate and transport 100-meter long steel structure truss. So you have to design in piecemeal, because most of these places are in a busy city center, and roads are narrow, trucks are smaller, you still cannot transport whatever can fit in the truck. That's all you can fit in. So for something like that, sometimes you need to even have some kind of shoring or staging structure. So these kind of trusses, one end of the truss can sit on the staging truss, and then eventually the shoring or staging truss comes out. But so along with that, that's another part of the use of steel, because during construction, you can't make a big concrete pier or something to support these kind of trusses temporarily. But it's very easy to build something, scaffolding kind of truss quickly. You can assemble this, take it out, and even rebuild or reuse. So there is great advantage. Even in concrete foundations, sometimes you need to provide the slab before you can backfill the structure, because the wall is not stable on its own, and at that time, temporarily, for some reason, you cannot erect the slab. Then it's easy to provide shoring supports, and it's much easier to do this with steel. So basically, a structural engineer can integrate cutting-edge designs and construction deliverables. If we understand what the goals are, it is really very easy to do the extensive analysis, and then even review to understand how the construction will be done, and include that also incorporate in the design. So what we typically, at Thornton Tomasetti, we have about a staff of 30 very sharp engineers who are very well versed with the software technology, and they are engineers also. And basically we call it our R&D group, and they are constantly trying to incorporate one software to other software, so we can save time and we can push our design limits. Because otherwise, if I had to sit and draw a very complicated curved structure, I'll be sitting and trying to draw on a board or trying to figure out the geometry from Excel spreadsheet. But the new trend is there isn't any time, so how we can incorporate all these so we can enhance our design and help the clients. So along with that, of course, with all these things, there are challenges we face. It's because we are in a transition phase. The fabricators, detailers, all the fabricators, details are not very well, they don't address these kind of deviations, because they are just used to working certain way, and anytime there is a change, it takes time to translate. But still, if we get everyone on board beforehand, it really helps. And eventually, once there are positive results, now the clients come back to us, and this is the only way they want us to proceed. More time? Still have time? Do I have more time? No. I have some other. Okay. This is something new we are developing, which we call it a parametric modeling. It's just something new we have been researching for last 12 months, and we feel like this is where the industry is going to move from now onward. show you some interesting slide. I guess engineering and construction is a little bit boring, so I'll just use some sunflowers. The reason for this video is basically what we are trying to say is that the sunflowers, all these sunflowers, there is a driver for these sunflowers, and the driver is sun, because as the sun moves, the sunflowers also move along with the sun. So in the last decade, following the development of the aerospace, we all know that the aerospace industry is way ahead of the standard AEC industry, and they basically do the parametric modeling. But unlike them, we just use computer-aided drafting. But now what we are trying to do is adopt this parametric modeling into our design. And basically, the way the parametric modeling works is because there is a driver. If you define one object, if you connect all the variables to one object, then it really, as you change one object, all the variables will change. And this just allows the architects, the very high-end architects, because they just sit there and they come up with all these weird shapes, and every time, next day they change the shape, and before we understand the geometry of their first design, the design is changing. So what it does is, this is still BIM, but what we are trying to do is we are trying to use the BIM in the concept design. Until now we are using BIM in the CD phase, so we know that the model will be used by the steel contractors and detailers. But now what we are doing is we are trying to use BIM for the structural engineers, so we can adapt to the geometry of complex structures. And all it does is, rather than spending the time later, we are trying to spend that time before. So this is one of the tower we had done. This was, the architect just had a vision of using ribbons, and he didn't even know what was the final, design he was trying to use. And we tried to look at connect all the variables to one driver, one object. So every time we change one, all the other parameters will change accordingly, and you can see the final evolution of the design. Go faster, because basically it is just a software we have written where it really helps them. This is in Basra. It's a 30,000 seat soccer stadium. And the architect, this is one of the leading sports architects in USA. And basically he wanted to have something like water. He sat down with us, and we are trying to develop what is something that he can vision, whatever he visions, we can even build it. And from that model, what he had visioned, we tried to take that model, we put the entire geometry together where we can efficiently locate all the columns, along with that the building facade, the roof, because this is not one of the common kind of structures. So not only you need to make sure that you can understand the geometry right, but then you can analyze it right too. And then we don't have enough time. So the only way to do some of these things faster is, if once you understand the basic concept, we can produce mass geometry, and we can incorporate it into SAP software, where we can, as an engineer, we can analyze and then send it to the steel contractors, where they can look into the fabrication. So these are just some of the images of some of these kind of complex structures happening nowadays. This one, as you can see, the facade was the biggest challenge. When the architect came up, there were like some 10 different variables of facade elements, and these things can get very expensive. This was in Basra, so it wasn't like it's in somewhere in UK or USA where technology is way ahead. So we had to come and think of it, and I believe a lot of the detailing was really done out of found in India. So what we were able to do is we were able to make all the parametric variables, and based on that we simplified the geometry, we reduced the number of variables, and we made out of 10, we can kind of, we were able to convince the architect that it makes 5, it still saves a lot of cost, and there wasn't much compromise of the design. So these are just the evolution of all the analysis. Then we had to worry about the entire transportation also, and all these things were developed based on the size, how much you can optimize. So, again, the brackets of every panel, there are millions of brackets, so we had to make sure that they can be all designed and fabricated also digitally. This is their fabrication plan. This is one of the confidential buildings. It's in Miami. It's a university campus. It's a very famous architect who has designed this. Again, he came up with the design, and in 2 months we had to release for mill order. And when you look at a structure like this, just to understand the geometry can take about 2 months. So we were able to finish our design because of this parametric modeling. We were able to generate the design and import into the SAP, which is a analysis software. One of the first building in New York City, and again it's a very complex glass building with a lot of facade variables, and we were able to provide this model to the architects. And every time one element changes, it can just, the computer will change, we can rewrite some of the numbers, and it can change the entire geometry. And just some of the projects that I So basically, the news now is that BIM is, growing arms and legs, and one will be left behind with using BIM only for construction documents in the next revolution. BIM will stretch into the new territory using 3D modeling to steel contractors will stretch our BIM models into construction phase of work. Using Rhino, Grasshopper, these are some of the latest tools which help to generate the design. We are stretching our modeling into concept design phase work, and no longer just a structural design tool, but BIM is finding application in optimizing the scheme design, fabrication, and construction. Since our firm is headquarters is in New York, I'll just give a very short brief overview of my company. We have about 550 engineers, and we have 22 offices. Majority of them are in US, and we have offices in China. We just opened office in Dubai and other Asian countries. We were working on 2,000 projects at a given time. Basically, we do building design, we do facade engineering, we do building performance, which is basically deals with existing buildings. The last few months, it's been pretty, our performance group has been very busy keeping up with New Zealand, Japan, property loss consulting, and construction support services. Thanks for allowing me to speak. sake, and